Okay, hi everyone. In this video, we are going to talk a little more about rate laws. So, I know earlier in this chapter I introduced the idea of a rate law, and now I'm going to work through a little more of the details about some specific types of rate laws. So, when we think about rate laws, the first thing that we really have to do is we have to narrow ourselves down to be thinking about what are known as elementary reactions. These are really kind of simplifying the processes that can occur in reactions. Now, the reality is that most reactions are a combination of different elementary reactions. So, if we are thinking about an elementary reaction, we can use the balanced chemical equation to determine the form of the rate law. And this is only true for elementary reactions. If we are working with a real reaction, a more complex reaction, then this stoichiometry relationship to the order of the reaction is not the case. And what do I mean by that? I mean that, remember that we said that nu is equal to K times the concentration of A raised to the X times the concentration of B raised to the Y. For this sort of reaction. And with X and Y, these must be determined experimentally. So, but if you look in this elementary reaction, we are able to take this stoichiometry from this 2 and put it as the exponent, as the order of the reaction. That only works because this is an elementary reaction. Okay? Okay, so now, if we have a first order reaction, we can say that the rate of the reaction is equal to K times A. This is an elementary reaction. We can also say that this rate is equal to the negative change of the concentration of A with respect to T. This is the other definition of the rate of the reaction that we defined earlier in the chapter. So if I put these together, I can say that this rate, this negative change in the concentration with respect to T, is equal to K times A. This is what is known as the differential rate law. And it's the differential rate law because we have this in terms of a derivative. Now, this derivative is hard to work with. And so what we do is we work to get rid of this derivative and turn this into the integrated rate law. And so to do that, we take the integral of both sides. And when we take the integral of both sides, you will see on this side that I have 2 terms that are d. And so what I want to do is I want to separate my variables. And so what we are going to work on is on this side of the equation, I have concentration of A, and on this side, I have T. And so we're going to work, so we rearrange so that we can basically multiply both sides by dt, giving us this expression. And now this is an expression that can be integrated. The integral of 1 over x is equal to the natural log of x. And so if I take the integral and I plug in the bounds of the integral, I get this expression. Then remember that the natural log of a divided by b is equal to the natural log of a minus the natural log of b. And so to go here, I applied the log rule. And then I just rearranged. And in this rearrangement, we get to this format of the equation. And this is what is known as the linear form. And I can get rid of the natural log, and it gives me the exponential form. So when we have this linear form, we call it the linear form because I have the natural log of the concentration at time t equals minus kt plus the natural log of the concentration at t equals 0. This is in the form of y equals mx plus b. And so this means that if I make a graph of time in the natural log of the concentration, that I'm going to get a line, and the slope is going to be equal to negative rate constant. And the intercept is equal to the natural log of the concentration at time 0. So if I have what's known as a second order elementary reaction, so this is where 2A would react to form products, I can undergo the same derivation process. So the first thing that I do is I set up the differential rate law, where I set the change in the concentration with respect to T equal to the rate law from the elementary reaction. And then I integrate both sides. I separate my variables. I integrate. And I rearrange. And in this rearrangement, I get the form, I get a linearized form. And so I can graph 1 over the concentration versus time. And in this one, I'm going to get a positive slope where the slope is equal to the rate constant and the intercept is equal to 1 over the concentration at time 0. Now, what's key to remember here is that this process is the same no matter what order of the reaction you're working with. We can find an integrated rate law for something that isn't not a elementary reaction order. So remember at the beginning of this, I said that most reactions are combinations. And so that means that there are things like third order reactions. There are things like 1/2 order reactions. There are very complex order reactions, and most reactions are that. So what we have to do is we have to think about how to go from the differential rate law to the integrated rate law, no matter what order of reaction we are working with.